So in this video we'll look at thermochemistry, which is the last little bit of fuels and heats reactions. Really it's the heats reactions part of it. What is actually called as thermochemistry, so sometimes that word is sort of skipped over at leave insert, called the heats reactions, but really it's thermochemistry, which is effectively the chemistry involving heat changes. That's the thermo part, like a thermo flask that measures or holds on to hot liquids or cold liquids indeed. Thermo's got to do with the heat, and then we're going to look at the chemistry, which is effectively the chemical reactions that occur. That's effectively what thermochemistry is. A lot of the time in chemistry we would refer to it as, just to give it some sort of, some sort of local meaning to us. You could think of it something like this little system here, where you have a system, and that system is like the chemical reaction, and the chemical reaction has surroundings, so that's everything around it, including, so if we were to say the system was the actual reactants in here that are in this conical flask, and then the surroundings would be the glass itself even, and indeed the air around it, and as you go outwards from it. So a lot of the time we think of heat changes, we think of that. So the system is essentially the reaction that occurs, so that would be in here, and then every reaction occurs in some sort of surroundings, and then the whole thing takes place in the universe. So that's effectively how we refer to it. So if you were adding A and B, two chemicals together, they will be the system, and then the glass, let's say there were two liquids or whatever they are, the glass that surrounds them and the air that surrounds them would be considered to be the surroundings. Now the boundary is normally the outside of the two chemicals, so that would be the liquid itself before it hits the glass even would be considered to be part of the surroundings. And what we try and study, now we've mentioned this before, but a couple of times I sort of maybe perhaps discussed it in some detail before, but effectively the heat of a reaction is the heat change of 1 mole of reactants as they go to products. That's effectively what it is. Now the heat of reaction is indicated, normally is indicated on just to the left of the chemical reactions. Now it indicates the number of moles of reactants and products effectively, because it's balanced, and the reaction reacts completely. So you see, we're going to look at two different types of reactions, and then we'll get into delta H. Now delta H is pretty simple to understand once you think about it. That's the heat change figure, if you like. These are the two reactions we'll look at. An endothermic reaction, these arrows are meant to represent energy being drawn in from the surroundings. Now you have to think about what that means in terms of what happens to the surroundings. If the surroundings are losing heat, let's say that this was a cube and you put your hand on it and the heat has been taken into the cube, well, your hand would feel hot or cold, and you need to think about that. It's the same principle that if you put a cube of ice onto your hand will feel cold. But the reason that is the heat in your hand, if you like, is moving into the cube as the cube melts. So the heat is being moved inwards. In the case of an exothermic reaction, exo means outwards, endo means within. So endothermic, taking in heat. Endothermic, thermic is the heat part, thermo, remember. Exothermic, animals that have an exoskeleton have a skeleton on their surface. Exothermic would mean that you give out heat to your surface effectively, to your surroundings really, but to keep it in the analogy of animals. So exo is to give out. So something like that would be the burning of anything in combustion. They're exothermic reactions. Energy is released to the surroundings when the products are formed. Thermochemical reaction equations indicate the heat of the reaction and the physical state So we always include this little small g here. That means a lot now. So as you go through chemistry, maybe the initial things, you could sort of overlook things, but for this it's really important that you would know that when you write a chemical reaction, when it's given to you, a thermochemical reaction, they should give the states. They have to give the states of the thermo. So it shouldn't be left out. That's a non-negotiable. And G stands for gas. S would stand for solid. L would stand for liquid. And AQ would stand for aqueous, or water, dissolved in water effectively. And here you see delta H is minus 484. I'm going to look at this minus figure. We don't ever have to remember the numbers, of course. That's not the point of this. We just have to understand this minus part. Now obviously you know bigger and smaller numbers, but not the actual numbers. This is the formation of water on the surface of platinum. So you can have the formation of water. And I think I looked at this reaction with you before in terms of surface adsorption theory. But hydrogen and oxygen, if you have them present and you have some finely divided platinum metal to increase the surface area of it, these gases will collect on the surface and adsorb to the surface, react to form H2O, and then H2O will evaporate off the surface or desorb again, which is interesting as a surface adsorption as well. That's not clear, you should look that up again. So now the minus figure is something I want to look at. Now you need to think about this, that when we're talking about reactants here, these are the two reactants, and this is the product here, water. And here you have delta H is minus. Now the minus is the thing I want to focus on. Kilojoules per mole. That's all that means. Kilojoules, you see it in the side of, it's a measure of energy. You see it in the side of cornflakes boxes sometimes. But in any case, these are the reactants and these are the products. Or this is the product. Now if it is minus, the direction of a thermochemical reaction is really, really important. That figure, that minus figure, stands for going from left to right. Now it's important because of what's known as reactions that can reach equilibrium. That's why I'm saying it's important. So it does matter, but it's always left to right. Therefore the reverse would be plus 484. But we never write that here. When you write this figure, you must write it beside a balanced equation. Otherwise it doesn't mean anything. Because you need to know what you're starting with and what you're ending up with. And this minus 484 is the amount of energy taken in when these products are formed. So that's the interesting thing. A lot of the time people aren't clear on that principle. They get it mixed up that that's the energy taken in to break the reactants or something. So just be careful when we write this number here, it's the energy change to form the products. To form the products. So in this case, it's minus 84. That essentially means that if I was to draw a diagram of that, there's the amount of energy the reactants have, if that was a little, and here is the amount of energy that the products have. My apologies, that minus would mean that the energy was given out. So this is an example of an exothermic reaction. But in any case, because it's minus, that means that the difference between here, which is the energy of the reactants, and the energy of the products, left to right here, is minus 484. So that difference there between this line here and this line here per mole is minus 484 kilojoules, or 484 kilojoules dropped, and that is lost to the surroundings. I'm putting this little peak on it here. This little peak here just means you might have to, for a reaction to occur, you might have to strike a match, or you have to lower the bond energy to allow these things to go forward to that. But in any case, I'm not too worried. I just want you to have a look at that minus figure. It's minus because the products have less energy than the reactants. It's the difference in energy, chemical energy I should say, between the reactants and the products. Going left to right, non-negotiable. Even if it's a reaction that can go back again. Very important to remember that as well. We'll have a look at them in more detail now in any case. The first reaction we'll look at both of them, but to look at an endothermic reaction first of all. And hopefully you saw earlier that if you had some sort of system, A plus B, like so, and it's endothermic, so there's your system, you add the two of them together, they will take in energy from the surroundings. Let's pretend it's in a bag here, to make C and D. But they will take in energy from the surroundings. So it's endothermic, taken within. Ammonium nitrate dropped in water. If you do that in a beaker, you feel the beaker getting colder. Sherbet and water. Sherbet's sweet. People eat those sweets because of the fact that they have a cooling effect. And photosynthesis is a nice, very obvious one from juniors here. Because you think about energy being taken in from the sun to make glucose and oxygen. So you see here an endothermic reaction. In the case of an endothermic reaction, it is so important, guys, that you remember that here, look at the reactants have less energy than the products. So what will delta H be? Remember, it's always left to right, going from reactants to products. If the reactants have less energy than the products, look at delta H. It has gone up. Now don't worry about this peak here for a second. We'll worry about that in a second. The main thing I care about is the difference between energy in the reactants here, which is down here. Remember, that's just a graph. As you go up, the numbers get bigger. As you go across here, time goes on, if you like. But the distance between these two here, these 2 points here, that difference will be positive. Because going from left to right, the products have more chemical energy than the reactants. Chemical energy. And you know that the law of conservation of energy cannot destroy energy, nor can you create it. Therefore, if the products have more energy than the reactants, they take it in from the surroundings. So it's endothermic. To take in is the endo part, and the thermic is the heat part. An endothermic reaction, delta H is positive because the reactants have less product. Well, actually, you probably better write that is that the products have more, to keep it positive and positive. Products have more energy than the reactants. So going from left to right again, remember, as you write reactants on this side and products on this side, energy goes up, positive. Endothermic reactions, chemical reaction that causes, we looked at endothermic, so now to look at exothermic. Exo is to give out heat, remember. Exoskeleton on insects and that, they have an exoskeleton. And thermic is the heat. A chemical reaction that produces heat is called an exothermic reaction. Example would be the combustion reactions of burning wood, respiration. These are all examples of exothermic reactions. So this is a nice example. You see, if we were to look at the reactants here, this is the burning of methane actually. If you were to look at there's the reactants. Methane that comes out of the taps in the laboratory and oxygen that is in the atmosphere. You strike a match. We'll worry about this in a second. The main thing I care about is the difference between this dash line. You see this over here. I'll tell you about this in a second. So essentially there's the amount of energy the reactants have. There's the amount of energy the products have. You see the energy has been lost going from the reactants to the products. They're like any loss is negative. And it's chemical energy in the chemicals. It's lost to the surroundings, remember. It's not destroyed. As you know from many